Hi, my name is Eric Yunkin, and today I will be discussing Kluster, an open source multi-beam sonar processing system that I developed over the last 2 years. First, a little background. Kluster is entirely written in Python and leverages the vast amount of tools and modules that are available in Python for scientific work. I used a lot of existing research and code from people within my group, including Glenn Rice, Jack Riley, Barry Gallagher, and others. Thanks to all of these people for their support and advice. The current implementation of Kluster is limited in scope, only supporting Kongsberg sonar formats, but the Kluster working data format allows for including other sonar manufacturers in future updates. Here is the Kluster interface. It includes a map view powered by the QGIS Python API that can display raster and vector data, shown here on the left side of the application. Here we see a depth raster product for the converted multi-beam data on top of the Google Satellite Web Map service. On the right is a points view powered by VisPy that can display the process soundings in 2 or 3 dimensions. We've selected the region of the surface that appears to contain a plane and loaded that area in the points view, showing the soundings in 3D. This interface is probably somewhat familiar to those of you who work with multi-beam, which leads us to the main question I get asked with regards to Kluster. Why develop a new multi-beam processing software package at all? There are several software packages out there that do this kind of work already, including SonarScope and MB System, both shown here. These packages can do much of what Kluster can do and more, having been developed over the course of many years by many bright people. In this presentation, I'll be discussing the 4 reasons that I have for working on a new multi-beam processing software package like Kluster. First, Kluster provides a new simple intuitive interface for processing called Kluster Actions. In this video, I'm going to demonstrate how Kluster Actions work. First, we drag a new multi-beam file into Kluster. After a brief delay as the Dask cluster starts, this new file is converted to the Kluster format. It is then automatically processed to get finalized data. Finally, we take our newly processed data and generate a gridded surface, determining the resolution automatically based on the depth of the area. We then load the surface layer to display the data in the map view, and that's what we see here, colored by depth. Kluster will identify that a new container is needed for this new file, given the date of the data and the serial number of the system, both automatically read from the raw file. Kluster Actions will appear as new data is added to the project, and as new options are selected or changed, such as the new vertical reference selected or a new post-process navigation data imported into the project. Kluster also provides a simple plotting widget that can plot all of the raw, intermediate, and final data variables in a number of different ways. Here we see an image showing the time versus sonar beam plot for the 2-way travel time of each beam. These plots allow the user to quickly view the data in different ways for troubleshooting and educational purposes. The main goal for Kluster processing is to make it simple and powerful, to ensure that anyone can get processed data quickly and easily from raw multi-beam data. The second reason is that Kluster provides a framework for experimentation and rapid deployment of new algorithms and routines. Here we see the Advanced Plots tool, which contains our commonly used sonar acceptance tests. These are Python scripts that provide us with statistics and guidance during the installation of new multi-beam sonars or evaluation of existing sonar systems. Here we see the accuracy test and the results plotted in new matplotlib figures at the bottom. The original implementation of this script involved processing in commercial software, exporting to a common format, importing into the Python script, and some additional work, all to get access at the multi-beam data. With Kluster, we can load and utilize the data directly in Python, allowing for a simple and more manageable routine. Kluster allows for quick processing and exporting to common formats, including LAS, which was used here by a user to compare LiDAR and multi-beam point cloud data in Esri software. Users can quickly get a processed dataset for the multi-beam data without extensive knowledge in hydrographic processing techniques. We can also run the processing steps in Python outside of the main graphical interface. Here is the result of a new tool we built to process archived multibeam data at the National Centers for Environmental Information using Kluster. This tool will automatically download raw multibeam data for the area of interest, in this case Corpus Christi, Texas, and process in Kluster. A link to the page containing the raw data files is shown at the bottom of the slide here. Being able to build Python scripts using Kluster allows you to use the processing system in new and interesting ways outside of the classical desktop environment. The third reason is to use new Python modules for scientific processing and cloud systems. Kluster is built around what is called the Pangeo ecosystem. Pangeo is a community-driven collection of Python modules built for scientific software, including Xarray for n-dimensional data analysis and Dask for parallel computation that can scale and integrate with cloud service providers. All of these systems are forward-thinking, and building Kluster in this environment will allow me to leverage their work in the future. Here we see 3 examples of ways to deploy Dask to the cloud, showing the global interest and excitement around Dask and scalable scientific applications. While Kluster is currently a desktop environment, I hope to evaluate this landscape for the best way to proceed with Kluster processing in the cloud. Kluster uses the ZAR library to write process data to disk. ZAR is a relatively new format that is purpose-built for archival in the cloud and for multi-threaded multiprocessing applications. I have found ZAR to be a reliable storage mechanism, and I have found that a number of people in the community have also found it to be so powerful that they are converting existing datasets to ZAR for more efficient access in the cloud and in multi-threaded processing systems. The final reason is to provide this new processing system in an easily accessible way. You can find the source code for this project on my GitHub using the link at the bottom of the screen. The README contains installation instructions for setting up the Python environment, but I would recommend you go to the Releases section to get the built executable, assuming you're a Windows user. I try to put out a new video about Kluster on YouTube every few weeks, where I talk briefly about one aspect of the system in detail. And finally, I have a short list of the features I would like to develop for Kluster in the near future. If you have any questions or suggestions regarding Kluster, feel free to pass those along in my GitHub or to me directly. Thank you for your time.